In this video, we'll be going over the second law of thermodynamics, and we'll be relating it to basically restating the second law as Gibbs free energy. So what this Gibbs free energy is kind of like this special equation that puts the second law all in terms of the system. So that's what it does. I'll write the equation after I write this one bullet point. So delta G, it's called Gibbs free energy. It allows us to apply the second law to chemical reactions or processes, since it puts everything in terms of the system. And so here's the equation. It's delta G equals the enthalpy. And notice there are no subscripts when I'm writing this. So that means everything is in terms of the system. And if this is done under standard conditions, you'll have a little degree symbol here, which usually it is. We'll be using tabulated data to get this, to get the values here, to predict the sign for delta G. So that's it. This is the same thing as the second law. It's the same as this equation. Delta S universe equals delta S for the system plus delta S for the surroundings. Okay, and so let me put a box or something around this. So okay, so that's our equation, and we'll be looking at well, let's actually see how it's connected to this. So if you divide each term by a negative temperature, so if we divide each term by negative T, then we get the following. We get delta G over T, negative, okay, equals delta H minus a T delta S divided by negative T. So we see that this term right here, or let's rewrite this a little by cleaning up that term. So we get delta G over T, negative delta G over T equals negative H over T, delta H over T plus delta S. Okay, like that. Now, since this term, this should look familiar, this right here. So delta H over T is actually delta S, sir. Okay, then we have the following. Then we actually kind of made it equal to this relationship here. So then delta G over negative delta G over T equals delta S sir plus delta S cis. Okay, and since this also equals okay, so since this equals this, okay, right here, then this right here will also equal this delta S universe. Okay, so this will also equal delta S universe. So by substitution, dividing by T, by temperature, we just showed that delta G divided by temperature, negative delta G divided by temperature equals delta S for the universe. Okay, and this is delta G for the system. Okay, it's always for the system. Okay, so this is like a handy little thing here to remember. And what this means is, I'll go over it on the next slide. I'm kind of out of space on this slide. So what does that mean, that relationship right there? So what that means is if If delta G is negative, then delta G is less than 0. Then delta S universe is going to be greater than 0. Okay, and this will always, if this ever happens, this process would always be spontaneous. Okay, remember what the second law is, entropy of the universe is always increasing. So if this occurs, then this chemical reaction or process is going to be spontaneous. Okay, and this calculated amount, is considered free energy, meaning it can be used to perform work, which can be used. So it's super useful to know this value to do work. Okay. If delta G is positive, then delta G is going to be greater than 0. So it's based on this, okay, which equals delta S universe. Let me rewrite that up here. So in this analysis, so if this were negative, okay, if you calculate, you get negative delta G, then we have negative, negative. This term would be positive. Now, in this situation, my next star that I wrote right here, delta G, we'll rewrite it again. Okay, and if delta G, if you calculate that value using this equation, okay, so if you calculate that value using this equation, okay, and you end up with a positive number, so let's say you plug a positive in for this, then this term right here is negative, and then delta S universe will be less than 0 because it's going to be negative. Okay, if that happens, if you ever get a positive delta G, then that process is going to be non-spontaneous. So if that ever happens, so then this chemical reaction or process is non-spontaneous. Okay, and this amount is must be supplied as energy to make whatever process that you calculated the positive G for to happen. So this amount must be supplied to make the positive delta G process work or happen. Okay, so there's a third thing that can happen. Delta G can be 0. So if delta G is 0, then that system is said to be at equilibrium. Okay, a very common time that this occurs is when okay, so like delta H and delta S must be opposite in sign and equal in value and equal. So these two processes are in balance. Okay, and a really common time when this happens this happens at a phase change. So I'll make a note of that because I'll special note because we'll do this later. So this occurs during a phase change. So I'll write during a phase change. Okay, so now we're going to look at the different cases for delta G, for the different things that can happen for delta G. This is just like what we did earlier in the other video, but this time we're going to look at it in terms of delta G. So you could have case 1. My C looks like a G. So case 1, you can have where delta H is exo, is negative, and the entropy of the system is positive, or more order formed, or more disorder happened. So it got more chaotic, the process or the system. Okay, so let's analyze what would happen to delta G. So you get negative H minus T delta S. So if this number is negative, okay, and you created more chaos or more disorder, okay, this value is positive, making this whole term negative. Okay, so you'll have negative plus a negative will always be negative. Delta G will always be negative. So delta G, if this is the combination, so if you have negative exo and positive entropy, then delta G will always be negative here. Okay, always. This will always be spontaneous. Okay, and spontaneous at any temperature. Okay, so that's case 1. We'll put this is spontaneous at any temperature. Okay, an example would be like something burning. Like a fossil fuel. Okay, so case 2. Okay, case 2 is where delta H is endothermic and delta S is negative, okay, or more order was created in the whatever process. Okay, so now let's look at our delta G equation for something that where these two events happen. So it was endo and more order form, so this term will be negative, making this whole term positive. So you'll have positive and positive, okay, and delta G, if that happened, will always be positive. So the result here would be delta G is always greater than 0, okay, and so if that happens, then for case 2, this is the result here would be non-spontaneous at any temperature. At any temperature. Okay, example of this could be, let's say like photosynthesis. Okay, so this is photosynthesis is endothermic, and it's making more complicated molecules. So it's building ordered structures from simple gas molecules like CO2 and water from the ground. Okay, so it's building ordered molecules, highly complicated ordered molecules. Okay, so this obviously photosynthesis needs an input of energy. and it gets it from the sun, of course. So let's go on to case 2, or sorry, case 3 here. So if we have case 3, then delta H is endothermic, which, as we have been seeing, is unfavorable, and delta S is favored, or more disorder, positive entropy. Okay, then delta G equals delta H minus T delta S. This will be positive. This will be positive, making this whole term negative. Okay, now we have opposing forces. So delta G, this will be spontaneous when this term here beats this term here. So when would that beat that term? It turns out it will happen at high temperatures, okay, to make this term beat this term. So this will be spontaneous at high temperature. Okay, because as you can see, when this goes up, okay, it'll make this term big, okay, and it will beat this term. Okay, this one over here. All right, so now for the next case, okay, when delta H is exothermic, but more so let me actually, I wanted to write an example here for this one. So an example for this would be like a phase change where more disorder is created, but it's endo. It requires heat to go in. Okay, so heat has to go in here for that to happen. Or when a liquid is being boiled. So again, heat has to go in, so we have endo, but it's creating more disorder over here as a gas. Okay, so also another popular time that this situation occurs is on endothermic mixing. That's another popular time that this occurs. So endothermic mixing. So for example, ammonium chloride, when this dissolves, okay, the flask would get cold, and it creates more disorder since it's mixing. Okay, so case 4, here's the last one, and this is when delta H is exothermic, and there's more order happening as a result. Okay, so let's write our equation. So delta G delta H minus T delta S. So this would be negative. This term right here would be negative, making this whole term positive. Okay, so now we need the negative delta H to beat the T delta S term. Okay, since this is negative and this is negative, okay, so the positive delta S term. So when would this beat the positive delta S term? At low temperatures. Okay, so this will be spontaneous at low temperatures. Okay, and example of this are the other phase changes. If you go the other way compared to before, so if you have a liquid and it's freezing to a solid, okay, then heat needs to leave, so we have exo, but more order happened, okay, and then the other one is true too. So if you go gas to liquid, it condenses. So heat needs to leave. Heat would be exo, okay, and more order forms. So it would be negative delta S. Okay, in both of those cases. Okay, and the negative delta S again, it makes this term positive. Okay, so that would happen at low temperatures, which, you know, if you think about it, it makes total sense because so when do these processes happen? Like when would something freeze? It would happen at a low temperature. Okay, when is something able to condense? When would something go gas to liquid? Okay, so when would that happen? Gas to liquid. Well, it would happen at a low temperature. Okay, would need to condense. Okay, so now for the your turn, okay, which is here. Okay, so I have these here. So make sure you guys are fully describing these. Okay, so fully describe delta H and delta S. Okay, and predict the sign of delta G. So sodium hydroxide is dissolved in a calorimeter, and you have this huge increase in temperature. Okay, so what does that mean? Okay, for delta H. So you have to think of the calorimeter. Okay, and then sodium hydroxide is dissolving. Okay, and then it got hot. Okay, so what does that mean? So if you have, in number 2, it says proteins fold by aligning hydrogen bonds and dipole-dipole forces of polar side groups of amino acids. So you have a protein, okay, and then it folds like that. Okay, so it folds over on top of itself like that, and then it's connecting hydrogen bonds here, here, here. Okay, so what does that mean? Okay, so fully describe delta H and delta S and predict the sign of delta G. So is it spontaneous? Is it always spontaneous? Okay, or when would it be spontaneous? Or is it always non-spontaneous? So which case is it for number 2? And then for number 3, which case is this? Okay, and this one actually asks you to predict delta H reaction and also look it up in the appendix and calculate it. So remember, so you have to write a balanced reaction and then look up these values in the appendix and calculate it. Okay, so that's the end of our tutorial.